Hello. Okay, this video will cover the kinetic energy, right? The part 2 of the kinetic energy. So we're going to solve the problems, except for 55, which is already in your first part, which is the lesson basically. A merry-go-round has a mass of that much and a radius of that much. And you just have to be careful. Sometimes this is given in centimeters, so you have to change it. How much net work is required to accelerate from rest to a rotational rate of 1 revolution in 8 seconds. So we learned in the past that work is equal to change in energy. Well, we're going to do the same thing here, except that this time we're not translating, we're not moving forward, we're just spinning. So this is just going to be K rotational. Okay, that's the network in this case here. Okay. So now this is going to be 1. So the work in the past it was F times D, right? This is just going to be, well, actually it was just asking us for the work. So it's 1/2 I omega square final minus omega initial square, because it starts from rest. We're going to ignore the other term. So it's going to be 1/2. So a merry-go-round, I think we can think of that as a disk. It's 1/2 m r square, okay, times omega. Okay, now we have to find out what the omega is. So I'll tell you what the omega is. Omega is 2 pi over 8, because it does 1 revolution in 8 seconds. Okay, so this is going to be 2 pi over 8 square. Okay, I mean a solid cylinder here or a solid disk is the same thing. And if you do the math here, you should get 17,005 17,005 plus 0.58 joules. Okay. Now let's just go back here and see what the omega is. So here omega initial is 0. It does 1 revolution, so which means delta theta is equal to 2 pi. And the time is 8 seconds. And we're trying to find the omega final. Right? That's what we're trying to find here. Yeah, I don't think that's 2 pi over 8. So let's see. I think we're going to use the equation that doesn't have acceleration. Yeah, we have to change this number. So this is going to be omega final plus omega initial over 2 times t is equal to delta theta. Okay, so this omega initial is 0. This time here is 8. Okay, so this should be divided by 4. Okay, so now and you can figure out, because this is going to be omega final times 4 equals 2 pi. So it's got to be 2 pi divided by 4. Okay, now let's look at 54. Calculate the translational and rotational speeds of a sphere, and the radius is given in centimeters, that rolls without slipping down a 30-degree incline that is 10 meters long when it reaches the bottom. Okay. So when it's going down a ramp, it's a sphere. When it's up here, it has only gravitational potential energy. So this distance here is 5 meters, because it's 10 sine of 30. This angle here is 30. Distance from here to down there, it's 10. So I'm going to write that mgh, that's the energy that it has up here, equals, now when it's all the way at the bottom, okay, it's translational because the center of mass, if you follow it, it doesn't rotate, it just slides. Okay, and the whole thing is spinning. Plus, now if you remember when we did the sphere, I gave you a shortcut in the previous video. So to find the 1/2 I omega square, you can just do the coefficient for the sphere times the translational kinetic energy. And I think the masses will go away. This is going to be 50 equals, so this is going to be half, and I think we can get rid of that. And a fifth, that should be 7/10 of V squared, and V equals 8.45 meters per second. Now to find the omega, we're just going to do V equals R omega, and omega is going to be equal to 8.45 divided by 0.2, not 20 I mean. So it's 42.26 radians per second. Okay. What is the ratio of the translational to rotational kinetic energy at the bottom? Well, I think we said in the past that kinetic rotational is equal to the coefficient, this is a sphere, K translational, right? Okay, so the ratio is 5:2 basically, right? Okay, I mean K rotational over K, what is it? So it's looking for translational to rotational. So K translational to K rotational is going to be equal to 5/2. So it's a ratio of 5:2. Okay. So it's going to be 5 parts translational and 2 parts rotational. Okay. Do your answers in A and B depend on the radius of the sphere or its mass? No, it doesn't, because if you remember, the mass canceled out over there and the radius canceled out over here. When you do 1/2 I omega square, this I is 2/5 mr square, and this omega is V square over R square. So the R is gone, and the M is gone after the conservation of energy. Now 55 I did in the previous video, so I'm going to skip that. So I'm going to go right to 56 and 57. Okay. A sphere of mass m, radius r, and rotational inertia I is released from rest at the top of an inclined plane. Okay. If the plane is frictionless, now keep in mind that without friction, that thing is not going to roll. Okay? Which means when you're doing the conservation of energy, just do mgh is half mv squared. Okay? So now this is gone. So the V just going to be a radical to gh. Okay. Now let's see what it looks like if there is friction. So if there is friction, it means there is torque, and if there is torque, it means it's gonna spin. So this equation is gonna look like this now. mgh equals half mv squared, and since all the answers are in terms of I, I'm not gonna do the sphere as 2/5 mr, 2/5 the translation. I'm just gonna say it's 1/2 I. Now omega is V over R, and we have to square both of this, right? So I think I can multiply everything by 2, so I'll get a 2 here, okay? And then maybe I can multiply everything by R squared, okay? I'll get an R squared here. I can factor out the V squared, so it should look like this. Hope you're following. And I can divide by that. And I can just take the square root, and that's my V. So the answer should be D. Okay. A disk, a hoop, and a solid sphere are released at the same time at the top of an incline. They are all uniform and roll without slipping. In that order, in what order do they reach the bottom? Well, the sphere is going to get down first, okay, because it has a coefficient for the moment of inertia of 2/5. That's the smallest of all three. And then the disk has a half and the hoop has a 1. So basically what this means is that sphere is easy to rotate. So it doesn't waste a lot of its time spinning. It just spends more of its energy getting down there than just spinning, because it's easier for it to spin. Suppose 59. Suppose a uniform. Did I skip 57? Nope, I didn't. Okay. 59. Suppose a uniform solid sphere of mass m and radius r roll without slipping. It doesn't depend on the mass and the radius. I think we saw that earlier. Every time we're going to do this conservation of energy stuff to find the linear speed, the mass and the radius will cross out. Okay. All right. This one here, it says we have to find the speed, basically, right? So how fast is the upper block? Well, the speed of this upper block has to be the same as the speed of this mass that's hanging. It's all one system. So I think gotta do the forces. So this is 20 newtons. I'm gonna call this one, just like I did in my notes, I think I called it T1. Yeah, I just want to be consistent. I call this T1. I'm gonna call this T1. Now, because of the pulley spinning, there is a torque, which means if this is rolling, if it's going forward and down, it's rolling in this direction, which means T1 has to be greater than T2. Otherwise, if they are equal, it will be no spinning. T2, T2, and there is friction here. Okay, and you have your 30 newtons here, and you have your Fn, which is also 30 newtons. So we're going to try to do this with rotational dynamics. What that means, we're going to use sum of the forces equals ma, and we're going to do the net torque equals I alpha. So for the first equation, it should be 20 minus T1 equals 2a. Second equation, which is up here, it should say T2 minus the force of friction. So, and the force of friction, I think I can just find out what it is. It's mu Fn, and the mu is 0.3 times 30. So that should be just 9, it looks like, right? Minus 9 equals 3 times A. Okay, now that's 3 unknowns, 2 equations, we can't do it. So we have to rely on the torque. Now the net torque is T1 minus T2 times, so it's basically the torque counterclockwise minus the torque clockwise. I can do it T1 times the radius minus T2 times the radius, or I can just factor out the radius. The radius is, it's got a diameter of 10, so a radius of 5, so 0.05 meters equals I, which is given, okay, times alpha. Now, A is equal to R times alpha, now which means alpha is A over R, which is 0.05. Now, if I take this 0.05, I can move it down here, right? I think I could do that, okay? And if I just add all these 3 equations, in my answer key, I didn't do it that way, I did it with substitutions, but I think this is easier. So if I just add, the T1 and T2 are gone, so I'm gonna end up with 20 minus 9, which is 21, equals, now, if we do the math here, so that's going to be 0.004 divided by 0.05 square. Okay, so it's 1.6 plus 3 plus 2, so that's going to be 6.6a. So a is equal to 13 point, 13.6 20 minus 9 is not 21, it's 11. Okay, that's why I got different answer. So 11 divided by 6.6, it's 1.67 meters per second squared, and that's, I think, what I have in my answer. Okay, yeah, I do. Okay, now we're going to do the old kinematic stuff. So we're going to do v squared, the all started from rest, plus 2a, and it traveled 0.6 meters. And I think if you do the math here, you should get 1.41 meters per second. Okay. Now let's try the same problem, but this time with energy. Okay. Now let's just say this is 1.6 meters above the ground, and this one here is going to travel 1.6 meters. I'm sorry, not 0.6. 1.6, not 1.6. Okay. So let's do energy. I think initially when you first start, okay, we have, this has potential energy, and this one has also potential energy. But I think the potential energy level of this one will never change. So I think we can just ignore the potential energy of that one. And I don't know if that's what I did. Yeah, maybe that's what I did. So I'm just going to ignore the potential energy of this because its potential energy never changes. So I'm just going to concentrate on this one. So I'm going to do m g h equals. Now this is going to have kinetic energy. This is going to have kinetic energy, translational, and the poly is going to have rotational. So I think it should be just 1/2. Now these two will have the same speed. So instead of writing two expressions for kinetic energy, translational kinetic energy for each, I'm just going to think of them as one. 5v squared plus. Now let's look at the poly. Now the poly is going to have, that's a disk, right? Oh, it's giving you the moment of inertia actually. So it's 1/2 I omega squared. Now V is R omega. So omega squared is V squared over R squared. Okay. But here initially we had friction. I think it says that there is coefficient of friction. So we have to add the work done by friction. Now, how do we find the work done by friction? Well, I think that's just going to be the force of friction, which I think we found it to be 9. Okay. So force of friction times the distance traveled, cosine of 180. Okay. And that should give us, if we solve this equation, we should get V equals radical 2, which is 1.41 meters per second. So here we cannot forget that there is friction on the flat surface. Okay, let's look at number 61. Yep. Okay, a pencil that is 15.7 centimeters long is released from a vertical position with the eraser end resting on the table. So it looks like this basically. So here's the eraser end, here's your pencil. Okay, the center of mass of the pencil is here. Okay, that's only half of 15.7 from the bottom. So it's L over 2. This whole thing is L. Okay, so now there will be no translation here. This is not sliding. It's just going to tip and fall. So we're going to do energy here. So the gravitational potential energy of the pencil is measured with respect to the center of mass. So it's going to be the mass of the pencil, G, center of mass is L over 2 above the ground. Okay, and that's going to be equal, that's going to all change to rotational because at the end, the whole pencil will be on the ground. So it's going to be 1/2 I omega square. So the I for something like this that's rolling around one of its ends is 1/3 m, the whole L square, omega square. So I'm doing 1/2 I omega square. So if we do this correctly, we should get 13.82 radians per second. Okay. So let's look at number 62. A hoop is rolling without slipping along a horizontal surface with a forward speed of 5.5 meters per second. When it starts up a ramp that makes an angle of blah, blah, blah. What is the speed after it had rolled 3 meters up? Now, the 3 meters is not the highest point. So this angle here is 25. So it goes up 3 meters. So now we don't care about the 3 meters. We just care about that height. So that's 3 sine of 25, if this is 3. Now it's rolling here, and it's a hoop, right? So for a hoop, I'm just going to do a dotted circle, kind of. And it's moving at a speed of 5.5 meters per second. All right. So when it's all the way down here, it has a translational kinetic energy, and it also has rotational, which is that coefficient for the hoop times translational kinetic energy. Okay. All that energy, when it's up here, is going to become rotational, translational, and potential energy. So it's going to be 1/2 mv square plus 1 times 1/2 m another v square plus m the g. Okay, I can probably put the g there. mg h, which is 3 sine of 25 degrees. So now let's see what we can do here. I think I combine this to okay, I think I can cross out the mass and combine at the same time. So I think this is just going to be v0 square equals v square plus 30, that's 3 times 10 sine of 25. Now this v here is 5.5 square. So I think by the time you finish with the math, you should get 4.19 meters per second. I just want to go back to 62. I just want to talk about one quick thing. If instead of a hoop we had a sphere, so you have a hoop going at 5.5 meters per second, and it's going to go up the ramp, or if you had a sphere, it's going to go up same ramp. If we think about which one is going to reach higher, and this is also going at 5.5. Now the hoop has to reach higher, and the reason for that is because in order to get the hoop to 5.5 meters per second, remember the hoop is lazy to rotation. It doesn't want to turn. It's got a higher coefficient. It's got a 1. A sphere has 2/5. So the hoop is going to require more energy, more work put behind it to get it up to 5.5, which means it's going to have more energy at the bottom. So the hoop has more energy at the bottom when it's going at 5.5 than does the sphere, which means this guy is going to go higher, because all that energy that it has down here is going to translate into potential energy. Okay. All right, let's look at this RT16. So this is a disk. It's initially rolling without slipping along a flat, level surface. It then rolls up an incline and comes momentarily to rest as shown. Okay, complete. Okay, so if this is a disk, its rotational energy is 1/2, okay, of its kinetic energy, of translational. Okay. So that should be 2 bars here. Okay, and I think I explained that. So K rotational is equal to that coefficient for the moment of inertia, or rotational mass, times K translational. Okay, and at the end, all the way at the top, it's only have it's going to have gravitational, and it should be 6 bars. 1, 2, 3, 4, 5, 6 right there. That's what it should look like at the end. Now RT17. Okay, so all of these objects start from the same height. So in other words, they have the same potential. They have the same potential energy, right? So on the other end, if this is frictionless, meaning like there is no work done by friction, they should reach the same height. There's no reason why they can get up there if there is no friction. So the answer should be all the same. And the reason is they started with the same potential energy. They should end up with the same potential energy on the other, on the second hill. All right, RT18. Objects moving down a ramp, speed at the bottom. Okay. Okay, so there's no friction on these blocks. So those two have to reach first because they don't waste, or they can't rotate. So there is no energy given to rotation. So it should be B and C together. Okay, first. And then a solid sphere has more mass closer to the center than a hollow sphere. A solid sphere, as a matter of fact, has a coefficient of 2/5. Okay. Hollow sphere, I think it's 2/3, but it doesn't matter. You have to know that if it's hollow sphere, the mass is all the way on the outside. It's like a hoop, but in 3D basically. So what comes next is going to be A, because it has less of a moment of inertia, and then D comes last. All right, and that should do it. Okay, for 78. Since it's asking for the coefficient of friction, we're going to have to use rotational dynamics. So we're going to write net torque equals I alpha. That's the free body diagram right there. Only the force of friction, which is mu mg cosine theta, because FF is mu Fn, and Fn is mg cosine theta, and that's equal to the moment of inertia of a sphere times alpha, which is A over R. And here we're missing an R because it's not just the force, it's the torque. So now this is going to translate to this mass is gone, all these R's are gone. So I'm looking at mu g cosine theta equals 2/5 A. Now we're going to do Newton's second law for translation, which is mg sine theta, that's the component of mg down the ramp, minus the force of friction, which is mu mg cosine theta equals m times A. So I think these m's are gone, right? So now what I'm going to do, I'm going to replace A from this equation here. So it should look like this: g sine theta minus mu g cosine theta equals 5/2 mu g cosine theta. That's what it should look like. Okay, so now if I move this to the other side, that should become 7/2. At the same time, I get rid of the g. Okay, so now it looks like mu is going to be 2/7 tangent of theta, and that's what I have here. Okay, the next thing it says, if mu were 0, would the speed of the sphere at the bottom be greater, smaller, or is the same? It should be greater, and the reason for that is because there is no energy being used up for rotation. So all the energy is translational. Let's look at number 79. So this is a sphere again. Determine the following for the sphere when it is at the bottom of the plane. It's translational kinetic energy. And we have to do it in terms of these quantities and only these quantities. Okay, so we start with mgh at the top. And at the bottom, we have translational kinetic energy. Okay, and we have rotational. And so the K rotational. Now I gave you a shortcut the other day where it says that K rotational is equal to that number for the moment of inertia times K translational. So I think so this should become 7/5. Okay, so if I move this here, it should become 5/7. Okay, yeah. So the K rotational, so the K translational is 5/7 mgh. And I guess the other 2/7 will go to rotation. So it's 2/7 mgh. Or if you don't see that, you can just do K rotational is 2/5 of that. And you should end up with 2/7. Okay. Determine the following for the sphere when it is on the plane. So if it's talking about acceleration, we're not going to use the energy. We're going to use equilibrium dynamics. So let me just say that the rotational kinetic energy here is 2/7 mgh, and the translational is, we said, I think 5/7 mgh. Okay, so to find the acceleration, I'm going to have to do dynamics. So the net torque equals I alpha. The net torque is just the force of friction times the radius of that sphere equals I for a sphere times alpha, which is A over R. Now this is net torque equals I alpha. Okay? The force of friction is mu mu mg cosine theta. Now we're going to do F net equals ma. So mg sine theta, because your mg is here, only this component here is helping you go down the ramp, or is responsible for going down the ramp. Now friction is going the other way. Minus friction, which is mu Fn, and Fn is mg cosine theta, and that should equal to m times A. Now we can cross out some A's from here, right? All these R's will be gone, okay? So now the same thing here, we can cross out these M's. And I think you can see that this is mu g cosine theta, so I can replace it. So, and here you have mu g cosine theta. So I can replace this piece here with 2/5 of A. Okay. Now if I combine this together, that should be 7/5. It should be equal 7/5 of A. So which means A is going to be 5/7 of G sine theta, and that's what I got. So A is 5/7 G sine theta. I think that's what it is. Yeah, okay. Now to find the magnitude of the frictional force, I think we can do is replace A. Yeah, so we're going to do this. Okay, so we're going to do mg sine theta minus this frictional force equals ma. And A is 5/7 G sine theta. So I did F net equals ma. So F, yep, that's it. Okay, so F is equal to mg sine theta minus 5/7 mg sine theta. So that should be 2/5 mg sine theta. 2/7, I mean. 2/7 mg sine theta. So the force of friction is 2/7 mg sine theta. Yeah, because this is going to be 7/7, so it's 2/7. Yeah. Okay. The solid sphere is replaced by a hollow sphere of identical radius. Of the hollow sphere, which is released from the same location at the same speed, rolls down incline without slipping. So it's still friction. What is the total kinetic energy of the hollow sphere at the bottom of the plane? Well, it's looking for the total kinetic energy. So it should be just mgh. Okay, because all your gravitational potential energy at the top is now in the form of kinetic energy. So this part here is just mgh. Okay. State whether the rotational kinetic energy of the hollow sphere is greater than, less than, or equal to that of the solid sphere. Now, if it's a hollow sphere, it means that it has a higher moment of inertia. And higher moment of inertia means that it's going to use up a lot of its kinetic energy, a lot more of its kinetic energy to rotate. So the hollow sphere will have a greater rotational kinetic energy at the bottom. All right, let's look at number 80. Here it says to derive an expression for the acceleration of the center of mass of the hoop as it rolls down the ramp. So I think we have to do like we did earlier in the previous problems. We have to rely on the dynamics. So this is a hoop. So the net torque, okay, which is basically the force of friction times the radius, equals I. Now the I for a hoop is mr squared, and alpha is A over r. Okay, so now I think all the r's are gone. So it should be F equals ma. Now we have to do F net equals ma. So mg sine theta minus the force of friction equals ma. So now I think if we just plug in ma here, so we'll be looking at mg sine theta minus ma equals ma. So this is equal to 2ma. Cross out the masses. So A is going to be half of g sine theta. And that's pretty much what I have here. Yeah. Derive an expression for the speed of the center of mass of the hoop when it reaches the bottom. So now we're going to do conservation of energy here. So at the very top, our energy is mgh, which is mgl sine theta. This is h. Okay, lowercase h. Okay, equals, at the very bottom, you have translational kinetic energy, but you also have rotational. And they're equal because the coefficient of friction, the coefficient of the moment of inertia for a hoop is just 1. So it's going to be same as the translational. So I think we can get rid of the masses. Okay, so multiply by 2, take the radical, so it should be V equals radical 2GL sine theta, everything under the radical. Oh, this add up to just 1 MV. Yeah, so there is no 2 here. Okay. Derive an expression for the speed of the center of mass of the hoop. So we're going to have to do conservation of energy. So mg, this h, which is basically L sine theta, equals 1/2 mv squared. That's your translational kinetic energy. But since the coefficient of the moment of inertia for a hoop is the same as is 1, so both kinetic energies are going to be the same, rotational and translational. So this is just going to be mv squared, and I can cross out the mass. So if you solve this equation, this is going to be radical GL sine theta equals V. Because these two add up to just 1 mv squared, you can cross out the mass and take the radical. And that's pretty much what I have here. Okay. Derive an expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. Okay, so now we're just going to do projectiles. Okay, so we have to figure out the time it takes to drop this high. Okay, so h equals 1/2 gt squared, which means t equals 2 uppercase h over g under a radical. Okay. Now, if we want to find that distance, so basically it's going to come here and it's going to do one of these things. So we're looking for this delta x here. Delta x equals the speed at the bottom, which is g L sine theta, times the time, which is 2h over g under a radical. So these are gone. So if you want to clean this up, it should be 2h L sine theta with a radical. Okay, that's what I got here. Okay, suppose the hoop is now replaced by a disk having the same mass and radius. How will the distance from the edge of the table to where the disk lands on the floor compare with the distance? The distance should be greater because the disk has less of a moment of inertia than a hoop. So when it gets down here, it's going to have a higher speed than this. As a matter of fact, if you try the math, you're going to find that speed you're going to find is bigger. So if it has a higher speed at the edge of that table, it's going to have to go further because the time of drop is the same.